Hi students, continuing our discussion of electrostatics for the fast track revision series for JEE Main. Now we are coming back to we are starting the electric field concepts. Now about the electric field, we have to understand why the concept of electric field is needed. Actually, electric force is an example of action at a distance. Already in the last video I have told electric force is an example of action at a distance. What is the meaning of this statement action at a distance? When two particles are there and they are placed at some distance apart, they are not in contact, then also they are exerting a force on each other. This is the meaning of action at a distance. Now what happens in this, when how this particular thing, one charge particle is exerting the force on other, this takes place in two steps. First thing, any one of the charge, say we are calling it as the source charge, this creates some electric field in its surrounding region. Here in this surrounding region it will create an electric field. This I am calling that this source charge is creating an disturbance in its surrounding region. This I am calling it as disturbance. Now when any other charge comes in this disturbed region, it experiences a force. So the first step is both of the charges are producing some disturbance in the surrounding region, and after that when other charge comes in this region, it experiences the force. Now this disturbance, when we are saying that it creates some disturbance in its surrounding region, this is actually the charge is creating an electric field in its surrounding region. And when any other charge comes in this electric field region, that charge experiences the electric force. Who creates the electric field? First charge. First charge creates the electric field, and that in this charge comes in that electric field region. So this will experience the force. So this way it takes place in two steps. Now here we define the electric field as the region surrounding a charge distribution in which the electrical effects of the charge can be experienced. This we call the electric field. The region surrounding a charge distribution, say some example, this is we have some charge distribution Q. Now due to this, some disturbance has been surrounded in this region. Then this region surrounding this charge, this entire region is going to be electric field region. Now this existence of the electric field, some basic factual points about this electric field you take. The electric field propagates from this disturbance. This charge particle created the disturbance. This disturbance takes some time to reach from here to here, or what happens? Or instantly it will happen. So electric field propagates with the speed of light. If electric field is, this charge is there, electric field has been propagated from this point to this point, then it is moving with the speed of light. Electric field travels from one point to other with the speed of light. Now electric field is just like a wave, you can say. It carries the energy and momentum with it. Electric field carries the energy as it is going from one place to other. It carries the energy and momentum with it. Now very important point. This charge is there. We are saying there are two charge particles which exert a force on each other, Q1, Q2. We have seen in the Coulomb's law, Q2 will experience the force due to Q1 and vice versa, 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Now, we are saying now, this Q1 creates the electric field and Q2 also creates the electric field. Now, say for example, Q2 is not there. Then no question arises of the force. If Q2 is not there, can we say Q2 is experiencing this force or Q1 is experiencing this force? No question comes about the force when Q2 is not there. But Q1 will still produce the electric field, whether Q1 is present or not. Say for example, Q1 is here. Here, the original location of Q2. Let us say Q2 is not there. Let us say Q2 is not there. Then in both the situation, whether Q2 is there or not, in both the cases, electric field at this location will be present. Electric field is independent of the existence of other charge to experience its effect. Electric field is independent of the presence or absence of other charge to experience the electrical effect of any other charge. Right? Now, another thing is, now whenever we are talking about any physical quantity, we have to represent its strength, like velocity. Velocity is more or less, so magnitude and direction telling. So same way, we have defined the electric field as the region surrounding a charge in which its electrical effects can be observed. Now the question comes, does it have any strength? Can we say stronger electric field, weak electric field? So there is, the strength of the electric field can be represented, can be expressed by three means. One is the vector physical quantity, a vector physical quantity which we call the electric field intensity. Second is scalar physical quantity which we call the electric potential. And third is a graphical way, visualization way. We draw some lines, etc., draw some graphs, etc., which we call the electric lines of forces. Now remember, electric field is the region, area surrounding a charge in which its electrical effects can be observed, while electric field intensity is the strength of that electric field, way to represent the strength of that field. People use this electric field intensity and that electric field word interchangeably. So be very careful in this, even though this is not required actually. Generally, electric field means they want to say electric field intensity only. So now we are coming to the electric field intensity. How to define the electric field intensity at any particular point? Now let us say in some region we want to find what is the electric field intensity at this point. Say in the surrounding system, here you have some charge distribution, 2-3 charge distributions are there. Any charge, it may be extended, it may be Q1, Q2, Q3, it may be point charge, whatever it is, these are the 3 charge distribution. Only for the example I have taken 3. And we are interested in finding the field intensity at this point. We want to find the field intensity at this point P. Now what we will do, we'll place a test charge. Test charge means a very small charge, a charge whose magnitude is so small that presence of this charge, presence of Q naught, does not affect the charge distribution on 1, 2, 3. So that presence of Q naught is not changing anything in space. That we are calling the charge, test charge. A test charge is a charge, point charge, whose magnitude is so small that it does not affect anything in the space. Right? So if we have to find the electric field at this point P, we'll place a Q naught here and find out what is the force experienced by it. What is the electric force experienced by this test charge? Then after finding this electric force, we will say electric field intensity at point P due to charge distribution 1, 2 and 3. Charge distribution 1, 2 and 3 together is equal to electric force Fe divided by Q naught, where Q naught has to be tending to 0. So we can say in short, electric field intensity at any point is defined as the electric force experienced by unit charge placed at that point. place a unit positive test charge, find out what is the force experienced. The force divided by that magnitude of that test charge will give you the electric field, right? Now, electric field intensity is a vector quantity. Its direction, like already we have written, electric field is equal to electric force upon Q naught. Q naught is positive test charge. So direction of electric field will be same as that of electric force. Now, another point you see, when a point charge is placed in an electric field, try to understand these words. When a point charge, let us say some electric field is there, and in this electric field one point charge is placed Q, then when in any electric field a charge is placed, it will experience the force. That force will be given by F vector equal to QE. When any point charge is placed in an external electric field, it experiences the force given by F equal to QE. Remember, it is a vector equation. If the positive charge is placed, if Q is positive, force will be in the direction of electric field. And if it is negative charge, then force is opposite to electric field. Again, try to understand. Let us say in this region some electric field is there and a point charge Q is there, plus Q. Then it experiences the force QE. If you have a charge minus Q is acting, then it experiences the force QE in this direction. Now, no need of writing the vector because already direction I am marking. So QE in this direction towards left, and here QE towards right. So if the charge is positive, force it experiences in the direction of electric field, and if charge is negative, it experiences the force opposite to the direction of electric field. Now we'll see the electric field due to discrete point charges and due to the continuous charge distribution one by one. First, we'll discuss the electric field due to point charge. Now, let us consider we have a point charge Q and we are interested in finding the field at a point P which is at a distance r from it. Then what is the field here we want to find? Then at this point we'll place a positive test charge Q naught. Find out what is the force experienced by it. From Coulomb's law we know that the force experienced is 1 upon 4 pi epsilon naught Q naught upon r square. So this force divided by charge Q naught, test charge, it is electric field. So it will become, if we see, Q upon 4 pi epsilon naught r square. About direction we'll talk. This charge is positive and this charge Q is positive, then force will be in this direction. So electric field also in this direction. If this charge is negative, then force will be in this direction. And hence the electric field also in the same direction. So we can say due to positive charge, electric field is away from the charge. And due to negative charge, electric field is towards the charge. Remember, it is an important point, conceptual point. So due to the positive charge, electric field is away, and due to the negative charge, electric field is towards the charge, right? So electric field due to a point charge, we can write it is given by kq by r square, where q is the charge, k is 1 upon 4 pi epsilon naught, and r square the square of the distance from the point charge to the point. So once again, if due to this charge we have to find the electric field at point P, due to this charge we have to find the field at this point, and this is positive, field is in this direction, equal to kq upon r square. If this charge is negative, field is in this direction, equal to kq upon r square. Similarly, we can write the electric field in the vector form also. That we are skipping. We already know what is the force divided by charge. We can write it as the electric field. So same way we can have the electric field due to a system of point charges. Due to a system of point charges, how to find the electric field? Now, what is the electric field? Force divided by test charge. Let us say you have the different charges here, q1, q2, q3, qn, and at this point you are interested in finding the field. Now you will bring a test charge here, find out what is the net force. Net force will be sum of the forces experienced by all the point charges due to this point charge, due to this, due to this, due to this, and so on. So the electric field will come out to be, electric field due to a system of point charges at any point is electric field at the considered point due to individual charges, and the vector sum of that will give you the net electric field at the considered point. So electric field at a point is given by the vector sum of the electric field due to individual charges. Here most of the things what we have discussed in the force, similarly you can solve the questions here also. You have to remember electric field intensity is a vector quantity. So when you are adding these things, if say for example you are having 2 point charges at a distance of q and 3q at a distance of say r, and you have to find the electric field intensity at a distance of r by 3 from here. Then first you find the electric field intensity due to the charge placed at A, which will come out to be in this direction away from the charge because positive, kq upon r by 3 whole square. And due to 3q, the field will come in this direction, E2, and E2 will come out to be kq upon k3q upon 2r by 3 whole square. Since E1 and E2 are opposite direction, net field will be E1 minus E2. This way you can solve, right? So in the next video, we'll discuss about the electric field due to continuous system of charges.